Okay, so let me show you how to get rid of the funky symbol thing that some of you have. So if you do a little drop down arrow and you have that it's like an I and then 2 dots. The way that you fix that is what I've got on line 9, but let me explain what's going on. So it's call names, that doesn't change. If I can type. Okay. The name of the data set you want to change. Okay. So call names. And then this is going to be data set. Okay. So it's basically I can change the column names. The little square bracket with the 1 stays. That means fix only the first column. Okay. So let's say in this Coral data one that I have. Okay. So you got to call it whatever you opened it as over here. Okay. Square brackets of 1 for the first column. In quotes, what you want to call it. So I could change mine to cheese. And then I changed it here to a different name. I would just tell you to spell it what the column name should be without the little symbol on it. Yeah, so that'll let you fix import issues. Since I know we're having multiple problems. And I have no idea why, because we literally never had this problem once last
Yeah,
semester.
I'm getting Chinese character on that.
Oh, what? Chinese? Yeah, I don't know why it's Chinese.
My screen doesn't look like that on the right. It's, yeah. Like, it's not over here. What? I was laughing. Oh, okay, thank you.
I was like, how did you even get that?
I didn't know either. So.
Okay, so you should be able to change the names of things. So correspondingly, if you wanted to do column 2, you would put a 2 there. You can actually do all of them at once, but generally the problem is with just the first column, so that's how you could clear that out. Okay. All right, so I'm going to keep adding to my script that we had last time, and we ended on assumptions. We're going to start with my favorite topic, which is effect size. Yeah. What'd you break?
We got a problem.
Okay, effect size. Woo! So this is especially important if you're in the graduate half, because this is what the meta-analysis project is about. So effect size is a measure of how big something happened in your experiment, basically. We ended with hypothesis testing. Hypothesis testing tells you if it's significant or not, but it does not tell me how much I should care. So effect size is how much of a difference between groups there were, how related are they. So our experiment worked, but how much should we care about whether or not it worked? So when we get into sample size issues with power, you could run zillions of people and everything would be significant, but then it might not be that important. So there are a lot of studies that use lots of people, and they're like, you should care about this thing, and then they have a really small effect size, and you're like, well, we shouldn't care that much. So it's a strength of a phenomenon. So I always think about it like, okay, something happened, how much or how big? Okay. If I can click. There we go. So we're going to talk about a couple different types of ones, and we're going to do some of them today with another program. So there's sort of 3 big types. Those based on mean differences, which is Cohen's d is the big one. Okay. So you'll use this anytime you have 2 or more means, t-tests, ANOVAs, post-hocs. Okay. And Cohen's d is the most popular thing that you'll see. Essentially what happens is it takes how far apart the means are and divides by the standard deviation. So it's a z-score. So some people talk about it as how much 2 populations don't overlap, but there's so much research on how people can't process negatives. So I always think about it as how different are they? So how far apart are the distributions, or how big is the distance between them? That we don't think about. Who in their right mind designed this stupid building with those stupid windows? Sorry, small rant. Like someone on acid painted it, right? And they're like, let's put all these glorious windows in so nobody can see or be comfortable temperature-wise in a classroom. So anyway, mini rant over on Monday. So, okay, some other types of effect sizes that are Cohen's D alternatives, Hedges G, and Glasses Delta. But we're just going to use D. So the kind of the guidelines for sizes, small, medium, and large is 2, 5, and 8, 0.2, 0.5, 0.8. So if you have an effect size of 1, that means there's a pretty big difference between the means. They can get very large, so 4 and 5 is not too unusual, and they can be negative. Negative just means one mean is smaller than the other. So most people report D as the absolute value because the negative doesn't really mean anything different than a positive. It just is the order that you subtract it in. The other big type that we'll do this year are variance overlap ones. So this is ANOVA again in a different way in regression. So there's eta squared. That's an eta. It may or may not have worked on your computer, which is a little curly in. Or r squared. I do not know why we have 2. They're the exact same formula. Like, there's no difference in the formula. They're the same damn thing. But sometimes people use eta, sometimes they use r. So it's based on variance overlap. So it's a Venn diagram. If I have IVs and DVs, it's how much they overlap in variance. If we're talking Cohen's D, okay, so mean of whatever group, that's N. This is Cohen's D, how far apart they are. So it's just 2 different ways to conceptualize how big the difference is, or how much the IV predicts the DV. But you have to think about them differently. So D is a Z-score that is measuring how far apart things are, whereas eta and R are percentages. O and omega. I forgot about omega. Okay. So eta and R are percentages, proportions. So it's 25% of the variance, that sort of thing. There's one more. It's omega. We're not going to calculate omega. Did I write on here? Yes. The formula is an evil disaster that we're going to avoid. And that's true. Omega is the old man's eta. So the joke is always you can tell when people went to graduate school by which one they used. So if you guys have Dr. Mitchell, who I pick on a lot, I teach stats in the fall, he teaches research methods in the spring, so everybody has to put up with us for a while. I think some of you guys in the back take him for behavior mod sometimes. Nope. Blank stares. Never mind. He loves omega. And I'm like, you can tell he went to graduate school at this time, and I'm much later. But it's still a variance overlap. It's the same idea as this. So if you ever see the little curly W, you can interpret it the same as eta. The formula is a hot mess. You'll most likely see eta with ANOVA and r squared with regression. I think the reason that happens is because at SPSS, when you run this, so the other software, it will give you etas for ANOVA and r for regression, so people think they're different, but they're the same exact thing. There are making up words now. There are partial versions. So you'll see NP2. Usually it's delta r squared. Or, ooh, I can't, wow, what is that? Omega. Partial just means it's one variable at a time. So when you have lots of variables at once, and you want to know what is the effect of just this variable, you'll get a partial. So I can calculate the effect size differently for each piece of the experiment, which is really handy. because the overall experiment might be significant, but only this piece is the important one. So, especially when we get into regression, we're talking about predictors, which predictor was the most important. Partial R squareds will tell you that. But we're going to start with CoSD because it's the easiest. The effect sizes for eta r and omega are sort of, it depends on who you talk to. These are the most common ones that I've seen. So 0.01, 0.09, 0.25. So they're totally different from Cohen's d. And remember, they're variance. So you cannot get an r squared of 2 or a negative 1. It ranges from 0 to 1. So that's 1% of variance, 9% of variance, 25%. Sometimes people do 1%, 6%, and 14%. So these are not set in stone. These are just kind of general rules. So some other options that you'll see for categorical variables, so like chi-square, are odds ratios. Right. So it gives you the odds of groups being in one group over the other. So odds ratios are the same thing as like the lottery. So what are the odds of getting this thing versus that thing? Or phi slash v, which is a statistic for chi-square. See below. Sorry, see later in the lecture. And those two are kind of based on Cohen's d. And when we get to chi-square, we'll do v. And those don't have very good size guidelines. They just are kind of a thing. You just kind of look at it and you go, hopefully that looks large to other people. All right. So we're going to jump into t-tests. I cut out z-scores because, oh God, I just don't want to do them. So we're going to do 3 different types of t-tests, correlation and chi-square for our basics review. I will tell you that I put up on Blackboard a new assignment. Oh, I could just pull it up on my computer. So this assignment doesn't have a due date yet because I don't know when we're going to finish the lecture. But it'll be due a week after we finish the lecture. But it starts with descriptives, that's what we did last week, and then now moves into what we're about to do. So the assignment is up. It's probably too small for you guys to read in the back, but so be sure you're going to the help desk. You're going to get an email from the help desk with all the hours. But this afternoon there's times. Tuesdays and Thursdays it's only in the afternoon, but Monday, Wednesday it's also right before class. So Shannon's there from 10 to 12, and then 11 to 12 on Wednesdays. And I would have said she was super lonely today, but we had somebody come by, so yay. And by come by, I mean it was a student that left my class and literally went straight upstairs to ask her questions. So please visit her so she's not bored. Because otherwise she's getting credit for doing nothing. Which would sound great, except that she wants to practice. So, okay. So let's start with single sample t, and then work our way through. So the point of t-tests is that you have not very complicated experiments. So with single sample t, we're going to have single independent, dependent. So in a single sample t, the independent variable really is this group of people versus the population. So you have to have some sort of population or control group or somebody to compare them to. The dependent variable has to be continuous, some form. So I have one group of people that I'm testing against a population mean, but I don't necessarily have a population standard deviation. And that, if you had both of those, you could do z. So for example, I think the one we're going to do is talking about SAT scores, so comparing our group of students' SAT scores to a national average. Okay, so anytime you have like a cutoff score or for you guys like diagnostic testing, like they have to make this certain, what's that stupid flexibility test name? It just jumped out of my head. No help in the back? No?
Flexibility of what?
There's like this flexibility, whatever. Fine.
Reach?
Well, no, never mind. It's going to come to me in like 2 hours and it'll be like, this is the name of it. Some of them have like cutoff scores, like you need to be above this or you need to work on do these exercises. Ah, see? That thing. So that has a cutoff score. So I can compare people's scores to that cutoff. Okay, that was a lot of work for that comparison. A dependency test, sorry, I should have written these in order. Right. Dependency test is still one group of people, but they're tested twice. So you kind of got time 1 versus time 2. It doesn't have to be time. It could be 2 different scales that you're testing them on, but generally it's kind of like a before and after is a good example. Yeah. Pre and post is a perfect example of dependency. It doesn't have to be time-based, but it is mostly about time. Your DV has to be continuous. So we can compare if their scores change between 2 testings. Independency is group 1 and group 2. Still has to be continuous. So on these, the IV is categorical. Until we get to correlation anyway. So the difference between really dependent and independent is just who is in each IV category. If they're in both IV categories, it's dependent. If they're only in one group or the other, it's independent. And that's going to be super important when we get into how we test these because the code literally is like one word different. So you can't go very wrong by running the wrong code. For dependent, independent, the math is pretty different. If you didn't have the population standard deviation, if you did, sorry, it would be a Z-score. Yeah. Like if you have IQ, you've got both. The population means 100, the standard deviation is 15, you would do Z. In this one, since you don't have a standard deviation, you do T. And because I used to talk about Z, and then I was like, no, I'm not doing that anymore. Because no one ever does Z. So, the assumption for t-test is that it has a normal distribution. So that means that the dependent variable is normal. So we talked about histograms last time. The fancy H word is homogeneity. It means each group roughly has equal variances, or each time point has equal variances. Single T, that doesn't count because there's no variance to compare to. So each group has equal variances, or each time has equal variances. And so we talked about standard deviation, roughly equal standard deviation. And then it's linear. Linearity is like a weird one. Do I have an example? No. So that essentially means if I have group 1 and group 2, and I'm making a graph of their means, the relationship here has to be linear, which is sort of a weird assumption because, of course it's linear. I've got one point and another point. I just connect the dots, right? Well, we're assuming that there's no like weird group 1.5 that they would still fit here, and they're not suddenly way up here, and it's parabolinear. And then after we finish this set of notes, we're going to do data screening, so we're going to cover these a lot more. So if this is sort of like, what is she talking about? You'll get it even more in next week. So linearity is that the relationship between the groups or the times is linear. Also that your data is not curvilinear. But when we're talking about groups, it's kind of like I have one and I have two. So. Okay, so that's for all of the t-tests. So we can kind of keep making our little table here. So it has to be normal, linear, and then homogeneous. First couple of weeks is like a spelling bee, if you weren't aware. Okay, so we're going to try a t-test now. Hopefully everybody has the data loaded. So we have our one group of people. It's a gifted honors program that they're trying to show is much better than the national average. So when you have a single sample t, you have to have some score to compare it to. That's called mu. And so their national average is 1250. So we'll see if it's different. So import the data set. You can call it whatever you want to call it since we've been issues. I think I had this typed out before and then I decided to change my mind. So I think I called it single t. And then here's the code. It says t.test. And we're going to use t.test all 3 times. We're just changing what goes in there. Column name, mu. So leave the word mu alone, equals, and then you fill in whatever number you have. Mu as a symbol is a like little squirrely U. But you have to type it out as mu. Mu equals. So that's just an example of the output. So let's try that. So I got t.test. My single sample t file is called single t, but you should type whatever the name of your file is. You should stop freaking out. There we go. Right. So I got single t. Oh, I need the column. So what's the name of my variable? It's SAT score. So I'm going to do the $sign. So the SAT score pops up for me. Comma, mu equals 1250. Don't just put comma at 1250 because it's going to think you want to compare it to a y of 1250 and it'll freak out. So be sure you leave the word mu equals in there. So we filled in this with the column name and this with 1250. Why 1250? Because this is what they said the national average was. $sign. Where? Here? Single T, $sign. All right. If you run that, you should get this slide. Hopefully. Right, so it's a single sample, one sample t-test at the top. And it gives me a bunch of numbers. Not too much confusion going on. Small confusion. His face is too bad. You're like, yeah, okay. Let's talk about what the output is now that we got a couple of little problems worked out. So the first thing it gives you is t. That's the calculation of the t-test when it does all the math, which we're not going to go over. Degrees of freedom. What the hell are degrees of freedom? So df is the number of scores that can change and keep the same results. So it's the number of scores that can change and keep the same results. In a single sample t, it's n-1. So we have 14 degrees of freedom, meaning we could change 14 of their scores, get the same mean and the same results. The p-value is the probability of getting these results if the null is true. To go back to the first couple slides, so 0.001. And it just tells you what you put in as mu here. This is a confidence interval, which we'll get to some other time. So you can ignore that right now, and then it actually gives you the mean. The crappy part is it doesn't give you standard deviation, so that you have to calculate yourself. So what do I do with all this crap? Right? Well, we talk about moat in a second. I'm going to skip a couple slides. I'm going to write this up, and I'm going to teach you guys APA style. The real difference between APA and I think you guys do Chicago AMA is the little number here is in subscript instead of parentheses. That's the biggest difference that I've seen. So if I take my output here, what I would do is just do T, and that's degrees of freedom, so that's where I got the 14 from, equals the T value. So 4.12. And then the P value. Feels silly to write P equals P, but so P value here. I did that one to 3 decimals because it was 001. Most people do 2 decimals, so if I had wanted to, I could have said P is less than 01, because that's true. Both of those would be correct. So what does that tell me, though? Okay, I have all these numbers. What does that mean? Well, remember our cutoff score was 5%. So we decided that if P is less than 0.05, it would be significantly different. And so is P less than 0.05? Hopefully this is an easy question. Yes. Some people have struggle with decimals, right? So P is less than 0.05. So yes, the honors gifted program at the school has a different average than the national average. And since it told me the mean was 1370, I would say that their average is higher. So 1370 is a bigger number than 1250. So it is significantly different. Yay. But is that an important difference? We'll see. And that's where moat comes in. Moat. There's lots of jokes. We are slowly writing moat. Moat is a program that our research lab wrote, or my friend who's smarter than I am wrote. It stands for measure of the effect, or magnitude of the effect, depending on who you ask in the lab. It's a Java-based program, so it should run on all of your computers with only minimal issues. And we're going to try it now. It is on Blackboard under Moat. So I think that's on Notes. Yes. Even if your computer says grump, grump, grump. It isn't zipped. Is it? Hold. Shouldn't be. Hold that thought. No, it's not zipped. It's a .jar. So you'll save it. And then I will help whoever, because I know we're going to have some issues. Yeah, I know it's executable. Ooh. Okay. I like that it gave me Bates Motel. So it should look like this once you get there. Okay, so what I have is I kind of cut and paste the screen of what it should look like. But if you actually are using Moat, okay, it will calculate Cohen's d for you. So you click on Measures, pick the measure you're interested in. I can't make that window any bigger, sorry. So single sample T. And then what I tried to do on the slides here is tell you what you have to enter. So I have to enter those 4 things to get an answer that's correct. So I have the sample mean was 1370. I got that from the t-test output. The population mean was 1250. Okay. What I don't have is the standard deviation. Okay, so I'm going to have to calculate that. Okay. So remember the code is SD, column name, na.rm equals true. So that's standard deviation. Just cutting and pasting it. Maybe. There we go. And then in. So how do I figure out in? Well, you could 2 different ways. So you can look at how many people are in the single sample T. So it says 15 observations, so that's in. Or if you aren't sure, remember the code for n is length, and then the column name.
If you spell it right.
Length?
Yeah.
Oh, yeah, I don't have it spelled right. You're correct.
Not necessarily.
Okay, so there's 15 people. And then 15. And now, once you're looking at it on your own screen and it's not super tiny, it will say that Cohen's D is 106. So that's a really big effect. So 0.8 is large, so 106 is a big effect. And it kind of shows you the 2 distributions. How can you tell that you've done this right? The T statistic will be close. So we had 4.12, and then in this, when you can see it yourself, it says 4.12. So this program will calculate Cohen's D and its confidence interval. So be sure you're just looking at where it says Cohen's D and not lower and upper. Okay. So in this window, it would be here. Okay. Right. Can I repeat what? Somebody say? Nope. Speaking now. Okay. So after I have that, I would write up, I have my mean, my standard deviation, T, P, and D. So anytime you write a test statistic, it needs at least 3 things. The test statistic, the p-value, and an effect size. And it almost always rhymes. So T, P, and D. Okay. I know, I've tried to come up with a good acronym, but I can't. So. Okay, let's see if we can get through dependent T since we're about 20 minutes, and then I will help you solve your remote problems, hopefully. Not life problems. I got plenty. I'm not that type of psychologist. Right. So for dependent T, it's anytime you have people tested twice, before and after scores, time 1, time 2, however you want to do it. Oh, we're going to get to do melt. Oh boy. Okay. Here goes nothing. Right. So my fake example, I have people's belief of the supernatural, which is appropriate since the X-Files was on again last night, but don't tell me anything because it's not on Hulu yet. Okay. So we had people test their belief of the supernatural before, and then we made them watch something, and now we're testing them afterwards. So high levels is high beliefs, and let's do dependent. So we're going to import the data set. So if you're looking at this data set, it's imported in what's called a wide format. Okay, I know it doesn't look very wide, it's 2 columns. But if I'm looking at my dependent T data, and then you also have your independent T data, you'll see the difference. Okay. So in dependent T, you have before and after, right, where each person has their own row. So like row 1 is before for person 1 and after for person 1. But it needs to look more like the independent T data, which is in long format, where each person has multiple rows. So I'll have before person 1 and after person 1, and they're all separate rows. So I've essentially told you never to open your Excel files, so we don't have problems with them. How can I fix that in R? Go back to PowerPoint here. So we're going to use a function called melt, which is what we're doing in here right now. It's so hot. Right. We're going to melt the data. So you should have, since you did the first assignment, you should have the Reshape package because ggplot installs it. But just in case you don't, you'll want to make sure you do. So click on Packages, and then make sure you have Reshape. Not reshape 2. Do not use reshape 2. Your life will be sad. Because it does not work the same way. If you don't have reshape, click install and then reshape. Even if you do, you could just overwrite it. Reshape. Not 2, just reshape. You need reshape. So now, be sure you load the reshape library. So do library, reshape. And I wish all reshaping was this easy, because then we wouldn't have to go to the gym. Right. We're going to take the data and we're going to melt it into a skinnier data set. So we have to call it something else. So what I'm going to do is walk through what's on this slide. But, studio here. So call it something else. So I always do the name of the data set with the word long after it, just so I remember which one's which, long versus wide. So long. The code is melt, open parentheses. It's data set name, so mine's called dependentee, so whatever you have yours called. And then I'm going to hit enter after the comma. So a lot of the code that you'll see me write will be stacked, and so it'll go across multiple lines. That makes it much easier to troubleshoot when you're having problems. And you'll notice, like, if you hit enter after the comma, R realizes, like, you're not really done with that line. So it moves it over for you and creates this, like, stacks it nicely. If you've ever done any type of coding, this is one thing they teach you to do, just so that you can see what you're doing. When we get to working with plots, this will be especially helpful. Okay. If you totally hate it and you think it's dumb, you don't have to, but it's easier to figure out where you went wrong if you stack your code. Yeah, because it can get very long. Okay. The second piece is ID. So ID is variables that don't change. Well, at the moment, I don't have any columns that won't change. I'm going to use both of them. But let's say you have 10 columns and you're only wanting to change 2 of them, you'd put the other 8 here. But we're going to leave that blank at the moment. So then what we're going to do is type measured equals, and we have more than one measured column, so we're going to concatenate or use the C function. And then type the names of the columns just like they're spelled in your data set. So if you've got that funky I symbol thing and you haven't fixed it, be sure it's in there. Okay, so, bonk. Mine are just before and after, so before and after. Okay, they do have to be in quotes. I told you it's wildly inconsistent when the quotes and when not. This time they do. So I've got melt, the data set name, comma, measured equals these 2 variables. Okay, you have to use the C function to keep them together. So let's try that and see what goes wrong. Hopefully nothing. It'll give you a little warning down here. It says using blank as ID variables. That's because we left it blank. That's okay. And then if you look at the data set by clicking on it, okay, now you should have it say before and after. And then a bunch of numbers. So it should be 1 column with your ID, 1 column with your DD. Oh, I hope y'all yeah. I have to close your other.
What was the?
Well, I did, but it said.
In my library.
So you have.
Did you get that?
Run both lines.
Try running it. Oh, how do you do that?
Okay, run the first one each time. And then So, something I didn't make obvious. If you're going to stack your code like this, you have to run both lines together. So if you hit Command Enter or Control R or whatever you're doing, just run one and see how it stopped. So I ran the first one, it has a little plus symbol here. It says, hey, you're not done. You gotta finish. Run the second one. Okay. Or you can highlight both of them together and click run up here. Whatever floats both. Sorry, old habits. Forget that I hadn't explained that. That solved most of everybody's issues. Yeah, don't run just the second line. What? That's fine. It's because we left ID line.
Oh, that's all. It's just warning. Okay.
She responded to it, and I was like, oh, why are you laughing? You'll have to test all I was like,
Okay, let's see if we can make it through dependency. Okay, yeah? 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 Little flags. He had his hand raised. Now he's ignoring me. Yeah?
Yeah, so after, can you go back to that script?
Yeah.
So after you type melt,
Uh-huh.
and then that comma,
Uh-huh.
what do you do? Just hit enter,
Yeah, that's all I did. So it should just...
and then on the 40, just double tap.
No, after I hit the comma, it auto spaced it over for me.
Oh,
Because it was, it knew I wasn't done.
okay. Nice.
Yeah. It does, once we get into some really complicated code, God bless you. Where was I at? Now she's distracted me. Once we get into code that's going to have lots of lines, this will help. Okay. Did that answer your question?
Yes.
Yes. Okay, good. So, dependency. So now that the data is in long format, we can do t.test again. And it's going to be a little different. Watch the time. Okay. Everyone has the tilde key on their keyboard, right? It's above the one, next to the one usually, to the left. Yes. Okay. Phew, no funky keyboards. Okay. So it's t.test. The name of the DV. Okay, so be sure you're using dependent t long this time. So it's DV name, tilde IV name. So I'm going to do dependent t, come here. So dependent t long. Now they're called variable and value because that's what melt automatically does. So variable is your IV, value is your DV. You can change the names of them, but you want to stick with DV is going to be value. If you do them backwards, believe me, you'll look at the output and go, what? It may not run actually. Okay. Oops, that's not a comma. Oh, it's a tilde. Sorry. It actually would run with the comma, but I don't want y'all to do that. So, okay. So I got dv is approximately. So the tilde says approximate this with, as in calculate the match. Predict this one with this one. But it always goes dv, tilde, iv. Okay. And then paired equals true. Or you can put the t. So paired equals true. So if you're doing a dependent t and you leave that part off, you will run independent t and you will get all the wrong answers. It's paired equals true. Whoops. That is totally not what I wanted to do. Hack. There we go. Okay, so I'm going to run line 1, line 2. And you should get it says paired t here. If you leave off paired equals true, it'll say, well, it's 2 sample t. Don't do that. Okay, so make sure when you're doing dependent t, it says paired t-test at the top. All right, so we should get this output, and then next time we'll talk about t-apply. So you can only do one. I'm scared of easy code at once. So you can start the homework if you want to try and play with it and get help. It's not due for a while, and then now I'm going to help everybody with their moat problems, hopefully. So if you don't have any questions, you can run away.